Okay, I'm recording this. I'll post this online today too. So really, we're just I'm just going to expand this out so that it's in polynomial form so I can do power rule. There will be another way to do this down the road. It involves what we call a U substitution. I'm not teaching you that yet. We'll get into that in section 5 of this chapter, actually. So if I expand that, if I square this binomial, I get 9 plus 6t squared plus plus 6t plus t squared. So now if I distribute, I get 9t squared plus 6t cubed plus t to the 4th dt. So now we have to do power rule on each separate term. I could write this as 3 separate integrals. That's not really necessary. You know that it's just going to be power rule for each term, right? So antiderivative of 9t squared is what?
Three t cubed.
3t cubed is right, because it's 9 times t cubed over 3, right? We add 1 to the exponent and we divide by that. Antiderivative of 6t cubed would be 6 times t to the 4th over 4. And then t to the 5th over 5. Or 1/5 t to the 5th, either way, plus the constant of integration. There's Max. Okay, what's another one you'd like to see?
24.
24. Hey, Max, don't forget to do the DMR. It's on Canvas. All right, sine x divided by 1 minus sine squared x dx. All right. So there's an identity. It's called the Pythagorean identity. How may I rewrite this denominator using that Pythagorean identity? Does anybody know that?
Negative cosine squared of x.
Well, it's actually just cosine squared. Because if it's sine squared plus cosine squared equals 1. So cosine is actually, it's positive cosine squared is 1 minus sine squared. So that's going to be sine x over cosine squared. And I think I did this one in the notes. You're good, Connor. I think I did this one in the notes. So I can break that up into sine. Can I break this also up into sine over cosine times 1 over cosine? So what's sine over cosine?
10.
It's tangent x, isn't it? And then what's 1 over cosine? Isn't that secant? And that's one of the ones you know. That's one of the 6 trig antiderivatives that you should have memorized. So what function has derivative secant x tangent x? It's all about the rewrites with these. What's another one? I'll do a couple more.
We do 18.
18, sure. So 18 is 3x minus 2 quantity squared over the square root of x. I'm going to write it as x to the 1/2. So if I expand this out on top, I get 9x squared minus 12x plus 4 over x to the 1/2 dx. All I did was square that binomial. Remember, you got to FOIL multiply that out. It's 3x minus 2 times 3x minus 2. And now what am I going to do when I divide each one of these terms by x to the 1/2? What am I going to do with my exponents?
Subtract.
That's right. I'm going to subtract them. When you divide powers with the same bases, we subtract the exponents. So 2 minus 1/2 is 3/2. 1 minus 1/2 is 1/2, and that'll be 4x to the negative 1. Now it's power rule. So add 1 and divide to the exponent. So if I add 1, that's 5/2. So it's going to be 2/5 times 4. Because you got to reciprocate. You're dividing by 5/2, which is multiplying by 2/5. 2/5 times 4 is 8/5. Add 1 to 1/2 is 3/2. So it'll be times 2/3. 2/3 of negative 12 is negative 8. And then once again, if I add 1/2, it's positive 1/2. It's multiplying by 2. It'll be 8x to the 1/2 plus a constant. Okay. Any of the application problems?
$31.
31. Okay. So for 31, they give me this. This is the given. That's the rate of change. That's the derivative. and they tell us, I'm going to pretend like 2012 is year 0. So they're telling us that in year 0, the population of cats was 100. We want to know how many there are in 2020. If I'm using year 0 as 2012, what year is 2020? What year would 2020 be? If I'm born in 2012, how old am I in 2020?
8.
8 years old. That's what we're trying to find. So P of T is going to be the antiderivative of this, right? P of T. So what's my antiderivative? Power rule again. Add 1 to the exponent, that would be 2, and divide by 2. And then negative 2t plus a constant. So if P of 0 is 100, if I put 0 in for both of these t's, what am I going to get from my constant of integration?
100.
100, that's right. So that's my function. And they want us to find P of 8. So let's just plug it in. I'll let you guys do the arithmetic. Okay. When you submit these to me, please do them as a PDF in a single document, not 12 different JPEGs. That makes my life a lot easier. I'll be more sympathetic that way. If something else comes up you have a question on after we get done today, just, message me and figure out something. All right, let's talk about the new. All right, these notes are in our module. We're going to start a section. It's going to take us like 4 days to get through these notes. That's why I want to get started today. That's why I wanted to go live today. I'm only going to spend about 10 minutes with you guys here, and then I'm going to let you go. How many times have I told you guys that derivative means slope or rate of change, instantaneous rate of change? How many times have we mentioned that? Just a couple, right? Maybe more than that. Probably too many to count, but antiderivative is area. This is what we're really going into. I showed you some tricks for doing the antiderivative here in this last section. Just basically the power rule, and we memorized the rules for all the different trig antiderivatives, but Now we're going to really understand what we're doing when we do antiderivatives. We've been doing what we call indefinite integrals, where we put a constant of integration on the end. We're going to start getting into definite integration, which means we're going to actually do integrals from one value to another, and we're going to be finding areas underneath a curve between two values, between two x coordinates. And the foundation for what we're going to be doing to show you the math that underlies this is going to involve limits and what we call summation notation. What we're going to be doing is we're going to be finding the area under a curve, under a function, by doing something that we call Riemann sums. And what Riemann sums are just really just rectangles, finding the area of rectangles that fit underneath that curve. We're going to start by using a finite number of rectangles. And then we're going to move to the infinite case, because the more rectangles we use, the more accurate the approximation of the area underneath the curve is. As a matter of fact, it becomes so accurate that for all practical purposes, it is the exact area underneath the curve. Just like we did with derivative, we kept picking points that were closer and closer together on the curve to get the rate of change, to get the instantaneous rate of change. If I pick 2 points that are infinitesimally close, for all practical purposes, that secant is really the tangent of the curve at that point. Well, same concept here. Instead of just using 4 rectangles, 10 rectangles, if I find the area of an infinite number of rectangles that fit under a curve, it's going to fit like a glove. It's going to give us that area. And a piece that works with that is this thing called summation notation, or we call it sigma notation. This is the Greek letter sigma. You have done this before. This is not the first time you're seeing this. Now, since you guys are 2 years removed from your Algebra 2 classes, some of you have only gotten this once, because I believe 2020, when we left in March, I think this was what was one of the things that got excluded from what we taught you at the end of that year. And we went that famous Friday the 13th, right? This was on the list of something we were going to cover at the end of that year, and we never got to it. But you did get this in pre-cal. So this is not the first time you're seeing this. So the way this works is this number on the bottom is my starting point. We call it a lower boundary. The number on top is my ending point. It's my upper boundary. And what we do is we start with this lower boundary. We plug it in our formula for whatever the variable is. And we keep going in increments of 1 until we get to n. This doesn't always have to start at 1. Wherever we start is where we start. Wherever this number is where we end. And then this symbol, this is the capital Greek letter sigma. That's why we call it sigma notation. Tells us we have to add all these terms up. We sum them. By the way, I put a little, anybody know what this little symbol is here? I'll give you a hint. It has something to do with this. Nobody? This is the lowercase. This is uppercase sigma. This is lowercase sigma. You'll see that if you have me next year in stats. We use that a lot. We use that for standard deviation, population standard deviation. Anyway, I don't know, maybe I'll be helping you. Maybe some of you joining fraternities or sororities next year, you'll have to memorize the Greek alphabet. I don't know. Not sure if that's a thing. So, on your web assignment, your first couple problems are going to be just like this. You're just literally going to be plugging the numbers into the sigma notation and calculating the sum. There's a way we can check these on our calculator. Okay, so I'm going to show you that real quick. On the machine. I'm going to do a regular share. All right, has everybody got my computer shared, my calculator shared with you guys now? All right, so in your math menu, if you go down one more spot, you go down to 0. Now, some of you might not have this. You'd have to have a somewhat newish calculator to have this. But if you have the newer calculator, this is our summation. And if you hit math 0, we can just type it in like it looks. So that first one was I goes from 1 to 6. And the formula was just I. Alpha I. And it does that for me. It's smart like that. If you have an older calculator, there's a way to generate it with a sequence. You wouldn't be able to actually get, you'd have to do the sum of the sequence. And I think, I was looking for it earlier. I don't. Let's see something. You can always go to your catalog. I can tell it to go to S. I forget the syntax here, but there's a way in which it might be like this. I'm going to try this. Might not give it what I want. Yeah, it does. So if you've got the older calculators, what you could do is the first entry in the sequence feature is your formula. The second is the variable. So my formula was I. The variable is I, start and stop, and it generates this. And then what you could do is you could first hit sum and then do the sequence, and it will actually sum that for you. That would be another way to do it. Not as convenient as the summation button, but if you've got an older calculator, at least that's another option. Or what you could do is you could store this in a list. And now when you go to your list editor, it's in there. And I could sum L1. So that's a plan B for those of you that have slightly older calculators. Okay. All right. So in addition to be able to calculate a sum using summation notation, we are going to get into some formulas that make some messy ones a lot easier to do. And I've shared those with you in your notes here. By the way, these properties that you see are the same properties that we did with derivatives, antiderivatives, limits. So these three properties are properties you've seen in other contexts before. Okay. And here are those summation formulas. And when we get into where we're going to head in this section, these are going to be very useful. Because if I had to crank these out by hand when I'm starting at 1 and ending at 25, no thank you. I don't want to do all that arithmetic. This is a much faster way of doing it. Okay. I'll save this for Monday. We'll start talking about these formulas on Monday. I'm not going to go through this example with you. But you'll be able to do the first couple problems in your web assignment with what I've already shown you today. With these couple of examples. Okay. Any questions for me? Everybody should have completed the DMR. You should be uploading assignment 4.1 worksheet before the end of the regular school day. Because I won't have a chance to look at those until this afternoon at the earliest. Any other questions for me? How many of you are going to go sledding today? It's going to be chilly. All right. That's all I got. Everybody, have a good weekend. I'll see you guys on Monday morning.
Hi, hoodies.
See ya.
Mr. Hodis, how do we turn the paper into a PDF?
I've done it on my phone with an app.
Oh, so is it like a way you save it? Like you can select all the photos and then
Yeah. And then you can like try to send it as a message and then it'll save as a PDF.
Okay.
If not, just send me just send it to me in a different format. But if you can, I would appreciate it.
Okay. See ya. Have a good day.
All right.
Odie, can we go through 16 and 23?
Let me end this recording.